You're sitting at a table with four cards spread out before you. Each card has a letter on one side and a number on the other. The four cards show DK, 3, and 7. You're told there's a manufacturing rule these cards must follow. Every card with a D on one side must have a 3 on the other side. Your challenge? Determine which cards you absolutely must turn over to verify this rule is being followed. Before you confidently reach for what seems obvious, let me warn you. This puzzle has humbled some of the brightest minds. Only about 10% of people get it right on their first try, and that includes mathematicians trained in logical reasoning. The correct answer is, you need to flip the D card and the 7 card. You do not need to flip the K card or the 3 card. If you didn't get this, you're in excellent company. This puzzle, known as the Wason selection task, was developed in the 1960s by psychologist Peter Wason. It's been replicated thousands of times across decades of research, and the success rate has remained stubbornly around 10%. But why is something that sounds so straightforward actually so fiendishly difficult? Let's break down the logic, card by card, and see where our intuition leads us astray. Starting with the D card, this one feels intuitive, and for good reason. Our rule states, if D, then 3. So naturally, we need to verify that any card showing D actually has a 3 on the flip side. Think of it as a logical containment. The set of all D cards must be completely contained within the set of all cards with 3 on the back. If we flip the D and find a 3, great. The rule holds. If we find anything else, the rule is violated. We definitely need to check this one. Now let's consider the K card, and here's where things start getting interesting. Our rule tells us, if D, then 3. But if K, then what? The rule says nothing about K cards. Maybe all K cards have 3s on the back. Maybe some do, maybe none do. The rule simply doesn't care about K cards at all. Whether we flip the K and find a 3 or a 4 or a 7, it has absolutely zero bearing on whether our D implies 3 rule is being followed. Moving on to the 3 card, this is where most people stumble. It feels like we should check the 3 card, doesn't it? After all, the rule mentions 3 explicitly. But here's the critical insight. Our rule states, if D, then 3. But it says nothing about if 3, then what? We know that all D cards must have 3s, but we have no idea what letters might appear on the backs of 3 cards. If we flip the 3 and find it doesn't have a D on the back, that's perfectly fine. The rule doesn't require all 3s to have Ds, only that all Ds must have 3s. If we flip it and do find a D, that's also fine. Either outcome is consistent with the rule, which means checking this card tells us nothing useful. Finally, we arrive at the 7 card, and here's the twist that separates the 10% from the 90%. Our rule states, if D, then 3. Now consider the logical contrapositive of this statement. If not 3, then not D. The number 7 is definitively not 3. Therefore, if we're looking at a card with 7 on it, the back absolutely cannot have a D, or else the rule is broken. This is why we must check the 7 card. If we flip it and find anything other than D, we're good. But if we flip it and discover a D, we've caught a rule violation, a D card that doesn't have a 3 on the other side. You might think professional mathematicians, people who work with formal logic daily, would ace this puzzle. Researchers Matthew Inglis and Adrian Simpson at the University of Warwick decided to test this assumption, and the results were humbling. 94% of all participants correctly identified that the D card needed checking, which is good news. But for the complete correct answer of D and 7, the failure rates were staggering. 71% of math students got it wrong, 57% of math staff got it wrong, and 92% of history students got it wrong. Even among those trained in mathematical logic, more than half fell into the trap. Common wrong answers included just D, D and 3, D with K and 7, or all 4 cards, which would work in practice but isn't the minimal solution the puzzle asks for. So if logical thinking is supposedly this difficult for humans, how does society function at all? Let's transform this puzzle into a different context and watch what happens to our success rate. Imagine each card now represents a person. One side shows what they're drinking, the other shows their age. The 4 cards display beer, coffee, 25, and 16. The rule is simple. Anyone drinking beer must be over 20 years old. Which cards need to be flipped? Suddenly, the answer becomes crystal clear to most people. Of course, you need to check the beer card to ensure the person is over 20. Of course, you need to check the 16 card to ensure they're not drinking beer. You don't need to check coffee because anyone can drink coffee regardless of age. And you don't need to check 25 because this person can drink whatever they want. Remarkably, 75% of people solve this version correctly. the exact same logical structure that only 10% solve in the abstract DK37 version. These puzzles are logically identical. Letter D maps to beer, number 3 maps to over 20, letter K maps to coffee, and number 7 maps to 16. Yet one feels nearly impossible while the other feels obvious. This reveals something profound about human cognition. We're not inherently logical or illogical people. Instead, we're extraordinarily good at reasoning about social rules, violations, and fairness, things our ancestors needed to navigate tribal life. But abstract logical statements divorced from practical context? Not so much.